Today we're going to talk about forces and Newton's laws. And we're going to start out talking about Newton's laws of force. It's interesting that before Newton and Galileo, what was thought about force and motion was really quite remarkable. Many believed that objects moved because they had an inherent desire or nature to move. Objects would seek their natural resting place. Thus, heavy things would fall because their heaviness was an indication of their desire to be at the center of the earth. Light things would rise. And there was no concept of forces in that time. So these things would seek their rightful place. Now this all changed as Galileo first came along, and he recognized that there was a relationship between speed, velocity, and acceleration. But the truly revolutionary findings were in the Principia, which was the landmark publication by by Newton, in which he outlines both the gravitational force as well as the three laws of motion. So the first law of motion states that objects will remain as they are until they are acted on by an outside force. So an object at rest will remain at rest. An object in motion will remain in motion at the same velocity until it's acted on by an unbalanced force. This introduces the idea of a force. A force is a pushing or a pulling action of one object upon another. It also introduces the idea of inertia. And inertia is the tendency of matter to resist changes in motion. That is, to resist being changed from a stationary to moving, or from moving to becoming stationary, or from moving at one velocity to becoming an object moving at a higher velocity. So the picture here, if you look at it very carefully, shows that the soccer ball will remain at rest until it's acted on by an unbalanced force, at which point it starts to move at a constant speed and direction until again it's acted on by an unbalanced force, which is shown here as the wind resistance. There's also the unbalanced force of gravity. Now let's talk about Newton's second law. Newton's second law states very simply, the force required to accelerate an object at a given rate is that rate of acceleration times the mass of the object. In a formula form, this is designated as F is equal to ma. And this formula is the one that you really need to memorize and keep available to do your homework problems and for upcoming quiz. The units of force are newtons, which breaks down to kilogram meters per second squared. If you multiply mass, which is kilograms, times acceleration, which is meter per second squared. In the English system, it's pounds, which is slugs per foot per second squared. Slugs is an old-time English unit for mass. Now what you can see is, if you in the picture here is if you apply the same force to two different masses, you get less acceleration if there's more mass, and you get more acceleration if there's less mass. So the force applied to an object is directly proportional to its acceleration. Another way to look at it is outlined in this diagram. Acceleration is directly related to force. So if you look at the guy on the right and the guy on the far left, you see that both of those have the same acceleration, primarily because he's applying more force with the increased mass. However, acceleration is inversely proportional to mass. So the two diagrams on the left here show the same force being applied, but you're getting less acceleration because of the greater mass. So let's take a look at a couple of problems. The first problem states that together a motorbike and rider have a mass of 275 kilograms. If the rider slows at a deceleration of 4.5 meters per second squared, what is the net force on the motorbike? Okay, if we look at this, we know that our mass is 275 kilos and our acceleration is minus 4.5 meters per second squared. And so the formula states that F is equal to ma, which is equal to 275 times minus 4.5. So that's minus a 1200 newtons to two significant figures. And the minus sign indicates that the direction of the force is opposite the direction of motion. The second problem states that a race car has a mass of 710 kilograms, and it starts from rest and accelerates to a velocity of 40 meters per second in 3 seconds. So the acceleration here is going to equal the change in velocity over the time, which is going to be 40 divided by 3, or 13.33 meters per second squared. So the force is going to be equal to mass times acceleration, which is going to be 710 times 13.33, or again, to two significant figures, you get 9,500 newtons. And so to two significant figures, it's 9,500 newtons. To two significant figures here, it's minus 1,200 newtons. Newton's third law of motion states that for every action, there is an equal and opposite reaction. And so when this person pushes against the wall with their feet, that's the action. The wall pushes on the feet and thus causes the system to move in this direction from right to left. When one object exerts a force on a second object, the second object exerts a force on the first object which is identical in magnitude and opposite in direction. Therefore, forces always occur in pairs. So let's take a second to review Newton's laws of motion. The first law states that objects will remain as they are until they're acted on by an outside force. And this introduces the idea of inertia. And inertia states that an object at rest will remain at rest unless acted on by an imbalanced outside force. An object in motion will remain in motion at the same velocity unless acted on by an outside force that's imbalanced. The second law states that a force required to accelerate an object at a given rate of acceleration is that rate of acceleration times the mass of the object. F is equal to ma. And the third law states that for every action there is an equal and opposite reaction, and that forces always occur in pairs.